Hello, everybody. So we're gonna, this is a continuation of talking about functions of several variables, in particular, two variables. And we are going to talk about something called level curves. These are a useful tool in a lot of ways, and one of the big ways we're gonna use them right now is to get, help us understand how these functions are operating and to possibly graph them. Right. So first, let's just sort of understand what a level curve is intuitively, and then I'll give you a definition, and then we'll find them for a particular function. So let's say I have some surface. Okay. All right. Level curves are going to be, if you've ever done any hiking, level curves are like how we get contour lines, right? What I would do is I can imagine taking a slice of this. Let's say this is some like mountainous island, and I can take a slice, and if you imagine a horizontal plane slicing through this three-dimensional object, I might get a slice that has a shape something like this. And if I sliced a little lower, I might get a shape that has something like this. And if I sliced a little lower, I might get a shape something like this. Right, and then maybe down here, there's something that goes all the way around, and so on and so forth. And I could draw these on a separate map, and so maybe starting with this bottom one, actually let's start with this top one. We have sort of an oval shape, and then we have a slightly bigger oval shape around it, and then we have a bigger one around that, and then it's also got a little one off to the side, and then there's a larger one containing both of them, right? And we start to get a sense, if you've seen contour maps, if you've ever gone hiking, this is what our contour maps show us, right? And they'll be labeled, so this might be, if this was a mountain, right, this might be 1,000 feet or something like that. And then this is 950, and this is 900. Let's see, this one would be at 900, and then this would be 850, let's say, whatever our scale is, right? And so you look at, it's a way to have a two-dimensional map, and you can tell, when you get practiced at reading them, you can read this thing and see this sort of shape emerging from the two-dimensional plane. So these are what level curves are, right? If you look at this, if this was now a function, if this surface was the graph of the function z equals f of x, y, these level curves would be like, for instance, this outside curve would be like the intersection between our function and the plane z equals 850, right? If I try to draw that plane in, if there's a plane at the same level as that bottom slice, imagine slicing that thing open, and that's exactly what shape comes out, right? And so that's how we're going to think about these level curves. So let me give us a definition. Level curves, so let's see, let's let z equal f of xy be a function. Level curves are curves of the form f of xy equals k, where k is in the range of f, right? So we pick a value in the range of f, just like we did here, right? I took 850, and we take that plane, or the way we would find the intersection is by setting our equation equal to it, and we'll find out what the curves are. So let's not dig into this definition too much. Let's just do an example. I think this will be very clear once we do them. So let's look at the function f of xy. Just separate things a little bit. So let's look at the function f of xy is equal to 5 minus x squared minus 4 y squared. Okay, so we're going to create some, well, let's do a couple things first. First, let's start with the domain, right? So this is just a polynomial in x and y. There's no numbers we can't square and add and subtract to each other, so there's no real big issue here. So our domain is going to be all of R2. Let's think about the range, right? I can maybe rewrite this as 5 minus x squared plus 4y squared. Notice this piece in the parentheses has to be greater than or equal to 0, right? It can't be any less than 0 because of those squares, which means our function is always going to be 5 minus some number, right? Which means f of xy is never going to be any larger than 5, right? When they're both 0, it's going to be 5, and it's also clear we can make x and y as large as we want, and so we can subtract huge numbers from 5 and go as far as we want in the negative direction. That seems to be the range of this function. Okay, so we've got our domain and our range. Let's make some level curves, okay? So what we're going to do is we're going to take, now that we know the range, we're going to pick values in the range and sketch curves at that value. So for instance, let's start with the level curve f of xy equals 5, right? So this is this piece of the definition. We take a number in the range. I'm using 5, and we get f of xy equals 5. Let's write this equation out explicitly. That means 5 minus x squared minus y squared equals 5. Which is another way of saying x squared plus 4y squared is equal to 0, right? Since neither of these can ever be negative, if either one of them was positive, it would be bigger than 0, and then you can't get back to 0 because the other one's positive. So this only has the solution 0, 0, okay? So that's the only solution we have there. So what I'm going to do with that solution, I'm going to make a little graph off to the side for my solutions. Oops. Okay. And that solution, oops, sorry, wrong tool. That solution is just this single point, right? This is for I usually write something like k equal to 0. That's the solution, the level curve for k equals 0, right? It's a point. It's not exactly a curve, but we'll accept that. It's still giving us information about the graph. So let's try another one. Let's try k equals 1. In other words, let's look at the equation f of xy equals 1, which is going to look like 5 minus x squared minus 4y squared equals 1. If we do a little bit of algebra on this, we're going to get x squared over 4 plus y squared equals 1. Okay, I'll let you work out the details of that algebra. But it's pretty straightforward to see. And you might recognize this as an ellipse. This is an ellipse that is going to go through, let's see, when y is 0, x is going to be 2. So let's mark it out here. Here, when x is 0, y has got to be 1. This is maybe not perfect, somewhere about here. Oh wait, let's try to make this. Let's see what tools we have. All right, so we've got an ellipse like this now. Okay, it doesn't have to be this nice, but this is easier to actually do on here. So this is going through the point. This is 2, 0. This is the point 0, -1. And this is the level curve for k is equal to 1. Okay. Let's do one more of these. Let's look at the level curve for k equal to -11. Okay. Now, how am I picking these numbers? Well, I'm actually picking them right now to work out to be nice. But in reality, you just have to pick some numbers if you don't kind of see what's happening. You just pick some numbers and see what you can do, if you can figure out what the graph in 2 dimensions are. Let's just do one more, and I'll say some more words about that. We've got 5 minus x squared minus 4y squared equals -11. If you do the algebra on this, you'll get x squared over 4 plus y squared equals 4. That's what, yeah. Which is, again, an ellipse. Or actually, we could make this a little bit better. Sorry, let's do one more step of algebra. Let's make it equal to x squared over 16, y squared over 4, and this is equal to 1. I think that's the more traditional equation of an ellipse. But in any event, that is still an ellipse, and we can graph that. And so, let's see, something like this, right? And this one's going through the points. This should be out at 4, 0, 0, 2. This is for k equals -11, right? Did I do that right? If I put in 4 for x, you get 16 over 16, 0 for y, you get 1. If you put in 2 for y, yep. So that's what our ellipse looks like, right? So already I can see a pattern that's happening, right? We started at the top of our range. The top of our range is 5. We are just getting a single point. It's like our graph is just touching that point and then moving downwards. And as we move downwards, we're getting larger and larger ellipses. So let's try to sketch what this might look like in 3 dimensions. Let's see. Yeah, let's actually draw the axes. I think that will be useful to organize here. Let's see if I can make, there's our x, there's our y. I'll move that into position. There's our z. Okay, and my origin's in the wrong place. Okay, so let's draw this with red maybe. So for instance, when z equals 5, we get the point 0, 0. So we get the point 0, 0, 5, right? Because that was the output equaling 5. So we're at that level. When we move down to, when we have the k equals 1 curve, so that's equivalent to the output being 1, we have this graph that's, right, so it's a little confusing because of the way we traditionally rotate these when we look at them. So this x coordinate out at 2, so we would come out to here and go back into the 3-dimensional space in the negative x direction. We get this ellipse like this. It's floating just 1 unit off of, 1 unit above the xy plane. And then as we move down to -11, so somewhere down here, we're getting an even bigger ellipse. And so if I try to connect these, I see that I'm getting some kind of upside down bowl shape that's going to extend, right? If we picked more values of k, we could fill in some more of these level curves and get that this thing is like, yeah, like a big upside down bowl, or the top of a hill, I guess. Instead of taking an upside down object, it's the top of a very smooth, smooth hill. Okay, and this is the process for level curves, right? You hope that you can make sense of the equation you're looking at, right? It's not necessarily obvious every time. We hope we have a nice catalog of equations under our belt. Let's do one more thing. Let's go to a nicer graph of this, of course. And I'm going to give my typical disclaimer. Of course, I know we can do this with computers. right? And I am going to, I give the same advice all the time. It is never a bad idea to get better at graphing. It is how we build the intuitions in our head to make the leaps that we're going to need to make when we're trying to, right, do new things that we don't already know about, or if we're trying to program things, we're trying to get the computers to do what we want. We have to have these intuitions in our head. And this is one of the processes. There's not a whole lot of shortcut to these intuitions other than, you know, learning how to plot points and all that kind of stuff. It forces us to dig in and work through these things. Okay, let's take a look at a nicer picture of this. Let's see. Okay, so here is that upside down cone, right, as I'm rotating around. The level curves, we were picking, so here is the plane z equals 5. You see just hitting our curve at the top. Oops. Right. And as I change, I'm going to change the values of k now, making them smaller. We see those intersections look like those ellipses that we were getting. So we were mapping each of these intersections, right? We had one at k equals, here's 1. Here's negative 11. It looks like it's off my, oops. There it is at negative 11, intersecting in an ellipse down there. And if we look at our graph from above, here is, let's get rid of the axes now. Now we're looking at it from above. As I lower the k value, we see these ellipses emerging. All right, so as I go lower and lower and lower, now it's stopped because it hasn't graphed below there, but for the parts that it's actually graphed, we see that as we get lower and lower, we get larger and larger ellipses, okay? And that's really what's behind these level curves we take, right? These are really just like traces we did in earlier videos, but we're just simply taking the output values to create something akin to those contour maps that people who hike are familiar with. Okay, that is it for this one. I'll do another example in some more videos, a couple examples, I hope, of maybe some trickier ones to graph. This is a pretty straightforward one. We'll see some trickier ones. Okay, thanks everybody. I will see you next time.